So it's really a great pleasure to be here, and I would try to give a very basic, say, talk, something that less than I give to my students, but I hope that it can be useful to have an idea of the tools and of what we can do with splines. So I apologize for the people that know everything much better than what I can say. So what I will build totally on the talk of Tom, and what we want to say to try to understand is how good, how well a function, if you have a function, say a smooth function to be simple, can be approximated by splines, by univariate splines. That's our goal. So first of all, maybe it is better to define in a different way, or to define a little bit again, what are splines? So splines are just, say, at least in what we are discussing here, piecewise polynomials that are connected in a smooth way. So let us write something. So you have, say, an interval, say AB, and you put some points inside. You have a partition of this interval. So you put some points, and let us give a name to that point. So let us say eta 0, eta 1, and so on, eta k plus 1. And then to this point, at least to the interior points, we also decide a regularity, a smoothness that we want to have. So let us say that this is regularity 1 at the first point, and then regularity 2 at the second point, and then regularity, say, k at the k points. So what we want to have is a function, and in addition, we decide the degree of a polynomial, say p. So the ingredients are the degree, the partition that we have on our interval, and the smoothness that we decided at each point. And so what we want is a function which is piecewise, so in each subinterval is a polynomial of degree at most p, and such that two pieces from the left and from the right, they connect with the smoothness that we have decided. And then maybe let me use this notation. So delta is our partition, so the eta, p is, okay, our degree, and let us say R, saying that R is all this vector, is the smoothness that we have. So what does it mean that a function, say, f, or even better, let us say small s, belongs to this space? It means that, do you see? I mean, because I don't see you. That's, I just do like that, then you see. Then what we have, the first is that if you restrict your function to, say, an interval eta I plus 1, then this belongs to the space of polynomial of degree less or equal than p. And then you want that if you consider S, then if you cross one of your points, say, then you have a continuity at least Ri, meaning that the function is continuous up to derivatives of order Ri. And this is true for all the points that you have. You just look at the interior. And so this is the intuitive, that's a way to define our space. But what is the relation with what we have seen this morning, as Tom mentioned? Because this morning we have focused on some special functions that there were B-splines, right? And so there is spline inside, so they must be related. They are B because they are beautiful, they are bell-shaped, they are a basis. There are many reasons why that function that Tom mentioned are B splines, the best. Well, there are many reasons. There are many reasons. Okay. And anyway, so what is the connection between, say, this space that I think is very easy to understand, and the collection of the splines that Tom mentioned this morning? This morning, Tom mentioned that space. Let us do that. S peak C. If you remember, I used that notation. What is this? This space is, say, a function is in that space. If you can write it in this form, linear combination of our B-splines. So is there any connection between these two spaces to understand? Actually, as Tom mentioned, there is a very nice connection. It is enough to select this Xi. You remember, maybe the Xi are just the sequence of nodes. You have just to select this Xi in a proper way. Of course, they must be related to all the parameters that we have to define our space. And the relation is quite simple. Do you remember? So Xi is a sequence, say, Xi1 up to Xn plus p plus 1, according to the notation of Tom. So what is the relation between these two cases? It is quite simple. What are our nodes? So look here. So you can, this is not the only way, but it's a simple way to do. So you start and you take eta 0, you take p plus 1 time. Okay, so I'm building up this sequence of points. What I'm writing here is just this sequence of points. So you start, so Xi1 is eta 0. Xi2 is again eta 0. And then Xp plus 1 is still eta 0. And then the next one is eta 1. You repeat. How many times? It seems a little bit strange, but it will be not strange if you think to the golden rule that Tom told you, is how many times? P minus R1 times. And then you go till eta k, you repeat this P minus Rk, and finally you put eta k plus 1, P plus 1 times. So altogether, you have a sequence of points. Well, we can count them. Okay, altogether they are n plus p plus 1, and this n still we don't know what it is. What is that? But okay, the p plus 1, here we have this p plus 1. So p plus 1 is this and that. So how many we have up to here? So what is our n? Our n is quite easy to compute. Start from the beginning, p plus 1 here. And then we have the sum of this plus this plus this plus that. And it is the sum of I from 1 to k, p minus ri. So that's it. What it is quite. Do you remember what Tom said this morning? So what is a B-spline? So what are these kind of functions? They are functions. They are piecewise polynomial of degree p. So this is done. This we have. And then we have to be sure about this, the smoothness, just to have the complete matching between the two spaces. And what was the golden rule of Tom? That the smoothness of our B-splines is given by what? By the degree minus the multiplicity of a node. Of course, what is the multiplicity, say, of these nodes? How many, the multiplicity is just how many times you repeat. So how many times you repeat P minus R1. So here, what regularity you have a P minus R1, so R1, which is exactly what we have. So, we are with this theorem that is known as a Curry-Schemberg theorem, the Curry-Schemberg that Tom mentioned, that the space with this relation between the nodes. That's the theorem. And why I mentioned that? Because this shows that the B-splines that Tom illustrated this morning to us actually are a basis, and a very special basis for this space we want to address. And this is why we can use this representation to represent any element of the space. And so we can use this representation also to understand how well a general function can be approximated in that space. This is our goal. And of course, I will not be, so I want to stay as simple as possible. So let us think that we have a function, say f, which is, of course, it's not a spline, is a function, which is smooth, just to be simple. Say, as an example, continuous with the derivatives up to a given order. And we want to understand how and if it's possible to associate to this function a function in either this space or this space. Now we understood that they are the same, so that the distance between this f and the approximating function is small. Whenever we need the distance, we need a way to measure a distance. So of course, there are several ways, but just to keep things very simple, let us consider the uniform norm. So the maximum of the absolute value, just to keep things simple. Okay, so this is our problem. So we have a function f, and then what we want to do, we want to associate to this f a function that I will call qf, and it will be clear in a while why I use this strange letter, q, which is an element of, say, our space, and possibly a good approximation of f. If my qf is an element of the space, it means that it will be possible to write it as this, meaning a linear combination of our function. And here I need some coefficients to have. Of course, if I want to hope to have a relation between f and this qf, this coefficient have to depend on f, otherwise there is not that much choice. So I will call these coefficients, say, lambda j of f. J just because it's the index and because they have to depend on f. I forgot to mention that whatever I'm saying is just in the interval AB. That's it. Our word is the interval AB, it's nothing more. So the question is, are there, say, ways to choose these coefficients such that, say, the difference between f and qf is small? And what does it mean small? How can we measure this distance? How can we bound this distance? Okay, I'm pretty sure. So as an example, it could be that QF is the least square approximation of F in that space, as so with a technique that everybody knows here. Or QF could be the interpolant to F in some points that we have. And these are reasonable choices, but we don't want to use these choices because in what we are saying, because their construction is a global construction, meaning to find the coefficients that we want here, you have to understand what is the behavior of your function on the global interval. Instead, we want to exploit the properties, the locality, the properties in terms of locality of B-splines. So I just recall from this morning that the BC of X is equal of zero whenever X does not belong to. And then I'm going to, it's too long what I'm saying. Okay, and then what we want to do, we want that this coefficient only depends on the behavior of our F for each J, on the behavior of our F in, say, that interval. It could be a little bit different, but just to simplify, okay? So we don't care to construct these coefficients. We don't care what is the behavior of F outside this interval for each J. We just focus on that. So this is a local construction. And then we ask, so this locality, so the properties that we ask for, so it's locality. Locality is in this sense that I have expressed. And then we ask for something else, boundness. What does it mean? It means that each coefficient, as you want to be able to bound it by a constant times the norm. When I write the norm is the infinity norm of our function where everything is local. So in the interval. This is one ingredient, and the last ingredient is polynomial reproduction. What does it mean? We want that if we have a function g, which is a polynomial of a given degree, say L, then we want that g and q of g is the same. That means polynomial reproduction. Okay, let me just show an example, just going back to the talk of Tom this morning. So assume you have a function f, then you associate, I use a different letter because it's a special, there is a special reason. So this qf I will call v, it's just an example. And this is defined as following, is sum over j of f of xi j p1 b j p xi of x. This is, in the notation of Tom this morning, is the average of the interior nodes of the B-splines. So this expression fits this requirement because locality, okay, of course, this is belongs to the interval xj plus p plus 1, of course. So locality is clear. And of course, we have boundness, right? Because we just take as a value, this is our lambda j. So we have that, of course, f of xj1, of course, is less or equal than the norm of f in the interval, because it's just one value. And can you help me? What about polynomial reproduction? Why Tom used that expression? Maybe you remember. Tom used that expression to give how to represent a polynomial of degree 1 in the spline space. So it means that if f is a polynomial of degree 1 actually used that expression to represent x, not a general polynomial of degree 1. A general polynomial of degree 1 is say, a plus bx. But we also have the expression for reproducing constant, which comes from partition of unity. So we have a polynomial reproduction of which polynomial? Of P1, of polynomial of first degree. So this is an example of this expression. So why I call this QF? I don't think I told, because these are called quasi-interpolant. Quasi-interpolant. So, and why, very quickly, why this, say, this requirement are good to understand the distance between, say, our function f and our QF. Very, very quickly, let us do that. So the goal now is, in this frame, to try to understand, this is our goal, where x is a point in our interval. So this is what we want to do. We want to have a bound here. So what we can do, we can go step by step. So the first part is, first of all, we can observe the following, that so x will belong to a given interval. I mean, an interval of the nodes. So it will belong to, say, an interval xm plus 1 of our nodes, because our nodes are distributed in the interval AB. And then what we have that QF of x is given by the sum. Actually, since x belongs in this interval, it's not that we have to use all the elements of the B-spline, because the most part of the B-splines, they are 0 in this interval. And then, as Tom mentioned this morning, it is enough to look at the p plus 1 B-splines, which are different from 0 in that interval. And so this is a strong reduction of the complexity of our. And now, very simple inequality, of course, this is less or equal than what? Than the sum. This, we have the lambda j of f. And here, I don't need the absolute value of the B-spline. Why I don't need? Because they are positive. And so, and then I can even have another bound. I can take the maximum over j of our lambda JF. And here, what does it remain? It remains just the sum of the B-spline, but now we can play the card of partition of unity. That's it. And now we can play the boundness, the card of the boundness that is on top. So we have a bound for each of these coefficients. So this for sure can be bounded by the norm of F. Actually, since I have many J, I have to consider all the possible intervals. And then this gives, this is just what you get if you put all together that interval, okay? This is the first. And then this is the first important result. And then, of course, what we have not played with yet, polynomial reproduction. It means that polynomial reproduction must play a role. Then what can we do? We can do this. So we consider fx minus qfx. X is still in this special interval. And then what can I do? I can take, say, any g, which is a polynomial of degree less or equal than L. And then this is f of x minus g of x plus q of f minus qg of x. Why this? Because g and qg is the same. Okay? And then we are done because, well, not really. I forgot to say something very important. The lambda, I want that they are linear. Otherwise, it does not work. So lambda are a linear expression in F. So it means that this is Q of F minus G. This is the important part. And now we are done because what can we say? This is, okay, f of x minus g of x plus, say, q f minus g of x. And now we are there. Look here. Just replace f with f minus g. So I can bound this with something like that. And then, of course, I can bound this as with, say, f minus g norm in, say, let us call this jm, plus what? Sorry, there was a constant here. I forgot. Cp. I'm going to finish. F minus g on the same interval. This is just that, replacing f with f minus g. And this means that this is 1 minus Cp norm of f minus g on Jm. As an example, what comes out there, in this case, this Cp is just 1 and L is equal to 1 as well. And then what is, and now, how do we close? Because it's lunchtime. And then, well, this works for any g, which is a polynomial of degree less or equal than L. And then if you have, say, and look, this Jm, look, this is an interval, okay, which consists of, say, some intervals by the nodes, some, but you can bound the number the number of intervals in terms of p, say 2p plus 1 or something like that, a finite number with respect to P. So you have that the length is less or equal than the maximum, say, I say H, times, say, I think it's this. H is what? Is the maximum distance between two. And then what you have? Which polynomial, as an example, you could choose? You could take, say, Taylor polynomial of degree less or equal than L. You expand in a point in Jm. And then with this polynomial, what do you have? You have that your bound can be enriched like that. This is something like the, say, H at L plus 1, derivative of order L plus 1 of F over Jm. And maybe you also have L plus 1 factorial here. It's just the estimate of Taylor polynomial. That's it. So it means that, I'm closing, this is for any x here. And of course, for any x in your interval, you can find a subinterval where it belongs to. So you see, you can, and h is the length of the maximal interval you have in your partition. So what you would like to have, you would like that this power is I, because h is small, right? And then you see that in our example it does not work so well, because this L was just 1, regardless to P. So it seems not a very good idea. But this is just a simple example. The ingredient is to find, say, way to construct these coefficients, lambda j, so that you have a polynomial reproduction of very high degree. And this can be done in several ways by using local interpolation or whatever. And I just want to conclude with the expression of the error that you can actually get. So in this situation, so assume f is of class CL plus 1 and L is greater or equal than 0, less or equal than P plus 1, then you can construct QF in this way such that F minus QF, the infinity norm, is less or equal than a constant Kp, H at the power L plus 1, derivative L plus 1 of F in the interval, say, AB. And what is good is that this is not only true for the distance between F and QF, but here you can put any derivative, and this is what you have. And R has to be 0 in that interval. And that's the power of Splines, and that's the power of quasi-interpolation. And close, this very important fact is Kp. It depends on P, but not on the knots. So it means it does not depend on how you select your partition. Also with derivatives. I see Uli is, because that's, so sorry for being long. It was too long. And if you are lost, you can find everything in the first chapter of this book, that also some of the material of top. Okay, thank you. Sorry for being long.